March 15, 1907, Rochester, New York. The city's Power Commission had reached a unanimous conclusion. Urban electrification required European-designed generators with the latest German engineering, high-speed turbines, maximum efficiency, constant upgrades to keep pace with growing demand. Across the industrial Northeast, municipal engineers followed the same playbook. General Electric promoted rapid cycling dynamos that promised cutting-edge performance. Westinghouse showcased compact turbine generators that impressed city councils with their modern sophistication. The prevailing wisdom was clear. Electricity was the future, and the future demanded the newest, fastest, most advanced equipment money could buy. Then Thomas Garrett, chief engineer for the Rochester Municipal Power Authority, stood before the city council with a proposal that contradicted everything the experts recommended. Not a high-speed turbine, not the latest German innovation, but a massive, slow-turning steam generator built to principles that dated back decades. A machine so over-engineered that construction costs would exceed every comparable installation in the region. The council members exchanged skeptical glances. Garrett's plan called for cast-iron components that weighed 3 times more than necessary, copper windings twice the required thickness, and mechanical regulators instead of the sophisticated electrical controls that other cities were installing. The generator would turn at just 150 revolutions per minute when modern units operated at 1,200 RPM or higher. It seemed absurd. Why build something so heavy, so slow, so deliberately outdated when electrical technology was advancing monthly? European manufacturers were introducing innovations that increased efficiency by 15 to 20%. American companies were developing compact designs that reduced installation costs dramatically. Every technical journal agreed that rapid cycle generators represented the inevitable future of power generation. But Garrett had spent 18 months studying generator failures across the Northeast. He'd examined burned-out bearings in Boston, cracked armatures in Philadelphia, failed regulators in Buffalo. He'd measured the microscopic wear that high-speed operation inflicted on every moving part. And he'd reached a conclusion that would prove more valuable than any efficiency calculation. The generators that worked longest weren't the fastest or most sophisticated. They were the simplest and strongest. The sketches he presented to the Rochester Council showed a machine that looked like it belonged in the previous century. Massive cast-iron frame sections bolted together with precision that would take months to achieve. Oversized copper conductors that would cost a fortune but would never overheat under maximum load. Ball bearings so large that 2 men couldn't lift them, turning so slowly that lubrication would last for years rather than weeks. The construction contract went to Pittsburgh's Consolidation Iron Works in April 1907. Not because they offered the lowest bid, but because they were the only manufacturer willing to meet Garrett's specifications without argument. While Westinghouse and General Electric engineers questioned the need for such conservative design, Consolidation's master pattern makers understood exactly what Garrett was attempting. The frame sections represented the first critical decision. Modern generators used steel frames fabricated from rolled plates, quick to manufacture and light enough to install without special equipment. Garrett specified gray cast iron, the same material that bridge builders used for components that needed to last generations. Each of the 8 main frame sections would be cast individually, then aged for 6 months before machining began. The aging process alone shocked cost-conscious observers. The casting sat in the yard, exposed to weather, allowing internal stresses to dissipate naturally. Modern manufacturers skipped this step entirely, but Garrett had seen what happened when unaged castings faced years of thermal cycling. Hairline cracks appeared, propagated, and eventually caused catastrophic failures that destroyed entire machines. When machining finally began in January 1908, Consolidation's most experienced craftsmen handled the work personally. Every bearing surface received hand scraping, a laborious process that created perfectly mated surfaces incapable of shifting under load. Master machinist Heinrich Weber spent 3 weeks on the main bearing housings alone, checking and rechecking dimensions with precision instruments that measured to 10,000ths of an inch. The rotor represented pure over-construction by contemporary standards. Garrett designed it with a diameter of 6 feet and a weight of 12 tons, turning at just 150 RPM to generate 60-cycle alternating current. Modern generators achieved the same frequency at much higher speeds using smaller, lighter rotors. But Garrett understood that mechanical stress increased exponentially with rotational speed. His massive, slow-turning design would last indefinitely while high-speed alternatives wore themselves out. The copper windings provoked the most controversy. Electrical theory indicated that conductors 1 inch in diameter would handle the generator's rated output with acceptable heating. Garrett specified conductors 2 inches thick, wrapped with double insulation, and mounted with spacing that allowed maximum air circulation. The copper alone cost $8,000, enough to buy 3 complete modern generators. Critics called it wasteful, but Garrett's reasoning was irrefutable. Copper failures destroyed generators permanently because rewinding required complete disassembly and months of work. Oversized conductors would never overheat, never stress their insulation, never create the hot spots that caused cascade failures in optimized designs. The mechanical voltage regulator embodied Garrett's design philosophy perfectly. While other installations featured complex electrical regulators with dozens of components, the Rochester machine used a simple flyball governor connected through mechanical linkages to adjust field current. No electronics, no precision adjustments, just reliable mechanical feedback that had worked for steam engines for half a century. August 1908 brought the massive components to Rochester's new power station on the Genesee River. The building itself had been constructed specifically for this generator, with foundations sunk 20 feet into bedrock and walls thick enough to support a 100-year structure. The investment seemed excessive to budget-conscious officials, but Garrett insisted that a machine built to last a century needed housing to match. The frame assembly took 6 weeks. Each cast iron section weighed over 4 tons, requiring careful positioning before craftsmen drilled and reamed bolt holes to ensure perfect alignment. The work couldn't be rushed. Every surface needed to mate precisely, every bolt needed to torque evenly, every measurement needed to verify within specified tolerances. Master mechanic Joseph Chen supervised the bearing installation with obsessive attention to detail. The main shaft bearings were massive bronze sleeves, 12 inches in diameter and 18 inches long, hand-scraped to create surfaces so perfectly matched that they would operate for decades on nothing more than a daily oil bath. Chen personally checked each bearing's alignment, measuring clearances that would determine whether the machine ran smoothly or destroyed itself through vibration. The rotor installation in September drew spectators from across the city. The 12-ton assembly required precise positioning within thousandths of an inch, with specialized rigging that Consolidation had designed specifically for this project. Once seated in its bearings, the rotor turned freely by hand, testament to the precision machining that eliminated any binding or unnecessary friction. The copper windings came pre-assembled on the rotor and stator, but their installation required meticulous attention to insulation and clearances. Each conductor passed through the iron core with spacing that prevented any possibility of short circuits, even under the most severe operating conditions. The connections used silver-brazed joints that would outlast the copper itself. The steam connection to the city's coal-fired boilers represented the final major system. Garrett designed the steam inlet with valves and controls that would allow gradual startup and shutdown, preventing thermal shock that could crack castings or distort critical dimensions. The throttle valve alone weighed 800 pounds, built to operate smoothly through millions of cycles without maintenance. The first test run on October 12, 1908, proceeded with calculated caution. Chen opened the steam valve gradually, watching as the massive rotor began turning, accelerating slowly to its designed 150 RPM. The generator's hum settled into a deep, steady note as the frequency stabilized at precisely 60 cycles. Voltage readings showed rock-solid regulation as the mechanical governor adjusted field current automatically. Within hours, the generator was carrying its first load, lighting street lamps across downtown Rochester. The machine that critics had called overbuilt and outdated was performing flawlessly, delivering clean, stable power that would continue uninterrupted for longer than anyone imagined possible. The first year of operation silenced every critic who had questioned Garrett's conservative design. Throughout 1909, the generator ran 24 hours daily, supplying power to Rochester's expanding streetcar system, downtown businesses, and residential neighborhoods that were converting from gas to electric lighting. Monthly inspections revealed almost no wear on any critical component. The bearing journals showed why slow-speed operation made such a difference. While high-speed generators at other installations required bearing replacement every 6 to 12 months, Rochester's massive bronze bearings showed only the slightest polish after a full year of continuous running. The oil bath lubrication system Garrett designed meant that fresh oil flowed constantly over bearing surfaces, preventing the buildup of heat and wear particles that destroyed faster-turning machines. By 1912, the generator had logged over 35,000 hours of operation without any unscheduled downtime. Other municipal power stations reported frequent outages as their modern generators failed from overheating, bearing failures, and insulation breakdowns. Boston's installation had already replaced 2 generators. Philadelphia was on its 3rd set of main bearings. Buffalo had experienced a catastrophic winding failure that left half the city dark for 3 days. Rochester experienced none of these problems. The massive copper conductors never exceeded safe operating temperatures, even during peak summer demand. The hand-scraped bearing surfaces maintained their precision under constant load. The mechanical voltage regulator adjusted smoothly through thousands of load changes without the failures that plagued electrical control systems. The 1920s expansion of electrical demand provided the ultimate test. As Rochester grew, the generator's load increased from its original 2,000 kilowatt rating to over 3,500 kilowatts during peak periods. Garrett's overbuilding margin meant the machine handled the increase without strain. The oversized conductors remained cool. The massive frame absorbed vibration without flexing. The slow-turning rotor continued its steady 150 RPM, regardless of load. Power Station Superintendent James Walsh kept meticulous maintenance records that revealed the generator's extraordinary economy. Annual maintenance costs averaged just $400, primarily for routine lubrication and inspection. Comparable installations spent $3,000 to $5,000 yearly on bearing replacements, rewinding repairs, and regulator adjustments. Over 20 years, Rochester's initial extra investment in overbuilt construction had been repaid many times over through reduced maintenance costs. The Great Depression. Years of the 1930s proved the wisdom of durable design when municipal budgets collapsed. Cities with modern generators faced expensive repairs they couldn't afford, leading to reduced service and brownouts. Rochester's generator continued its reliable operation on minimal maintenance, budgets requiring only basic lubrication and routine inspection that existing staff could provide. By 1940, the generator had operated for 32 years without major overhaul. The original bearings still ran smoothly. The copper windings showed no deterioration. The cast iron frame remained dimensionally stable despite millions of thermal cycles. Meanwhile, most installations from 1908 had replaced their original generators multiple times, unable to maintain equipment that wore out under the stress of high-speed operation and optimized construction. The end of World War II brought revolutionary changes to electrical generation. New materials, advanced cooling systems, and higher operating speeds promised dramatic improvements in efficiency and power density. Manufacturers showcased generators that produced 3 times the power in half the space, running at speeds that would have been impossible with pre-war technology. General Electric's 1947 catalog featured streamlined generators with aluminum housings, forced air cooling, and automatic electronic controls. Westinghouse promoted compact units that weighed 60% less than traditional designs. The technical specifications impressed engineers trained in the modern efficiency-focused approach that dominated post-war thinking. Rochester's Power Authority faced pressure to modernize. The 1908 generator, now nearly 40 years old, seemed hopelessly outdated compared to sleek new machines that promised better performance at lower cost. Consulting engineers recommended replacement, arguing that old equipment couldn't meet modern standards for efficiency and reliability. But Walsh, now chief engineer after Garrett's retirement, commissioned a detailed analysis that told a different story. The 40-year-old generator's efficiency remained at 92%, only marginally below the 94% that new machines claimed. More importantly, its actual operational costs, including maintenance and downtime, came to just $0.20 per kilowatt hour, while installations with modern equipment averaged $0.01 when all factors were included. The comparison became starker as post-war generators began showing their weaknesses. The higher operating speeds that enabled compact designs created severe bearing wear that required replacement every 2 to 3 years. Aluminum housings that reduced weight also reduced thermal mass, leading to overheating problems during peak loads. Electronic controls that simplified operation also created new failure modes that required specialized technicians to repair. Rochester's generator continued its steady operation, while newer installations struggled with problems that illustrated the cost of optimization. A 1948 Westinghouse unit in Buffalo failed after just 18 months when its high-speed bearings seized, causing $45,000 in damage. Syracuse's 1950 GE installation experienced repeated electronic control failures that caused 6 major outages in 3 years. The Korean War-era demand spike of 1951 to 1953 provided another crucial test. Rochester's generator handled sustained overload operation that exceeded its original rating by 40%. The oversized components that critics had called wasteful absorbed the stress without difficulty. Newer installations that operated closer to their design limits experienced failures that caused extended outages during critical peak demand periods. By 1960, the economics were undeniable. The 52-year-old generator had outlasted 3 generations of supposedly superior replacements. Its operating costs remained lower than any modern alternative. Most remarkably, it still ran on its original bearings, windings, and mechanical components, while contemporary machines required major overhauls every decade. The vindication was complete when General Electric engineers visited Rochester in 1962 to study why the ancient generator remained reliable when their modern equipment failed so frequently. Their report concluded that Garrett's conservative design philosophy had been correct all along. Slow speeds, oversized components, and simple mechanical systems produced better long-term results than optimized performance and advanced complexity. The 1970s brought computerized control systems and turbine speeds that reached 3,600 RPM, promising efficiency gains that would finally make slow-speed generators economically obsolete. Digital monitoring systems tracked every parameter in real time. Advanced materials allowed higher operating temperatures. The engineering consensus proclaimed that modern technology had finally surpassed the limitations of mechanical design. Initial results seemed to validate the optimism. High-speed generators produced more power per ton of machine weight. Computer controls optimized performance automatically. Solid-state electronics eliminated the wear issues that plagued mechanical regulators. The future appeared digital, fast, and sophisticated. But reality and operating environments told a familiar story. The electronics that enabled advanced performance also created new vulnerabilities. Circuit boards failed from thermal cycling and electrical transients. Computer memory corrupted, requiring complete reprogramming. Sensors drifted out of calibration, causing shutdown sequences that interrupted service. The very sophistication that impressed engineers in laboratories became expensive problems in continuous operation. The planned obsolescence built into electronic systems proved even more damaging to long-term economics. Control system manufacturers updated their designs every 5 to 7 years, discontinuing support for older models. When critical components failed in 10-year-old generators, replacement parts were often unavailable. Entire control systems required replacement at costs exceeding $200,000, turning routine repairs into major capital expenditures. Rochester's 1908 generator continued operation through all these changes, now managed by engineers young enough to be Garrett's great-grandchildren. The mechanical regulator that had seemed primitive in 1908 remained fully functional in 1980, requiring only basic maintenance that any technician could provide. No obsolete components, no discontinued parts, no software updates, just reliable mechanical operation based on principles that never changed. The contrast became dramatic as failed high-speed generators went to scrap, while the century-old machine continued earning revenue. A typical 1975 installation might operate successfully for 15 years before electronic obsolescence and mechanical wear made replacement more economical than repair. Rochester's generator passed its 75th anniversary still running on its original components, proving that proper initial design mattered more than technological sophistication. The 1990s digital revolution intensified these patterns. Generators with embedded computers and network connectivity promised remote monitoring and predictive maintenance. The reality included software bugs, compatibility issues, and cybersecurity vulnerabilities that earlier engineers never imagined. Each advance in sophistication added new failure modes without fundamentally improving the basic function of converting mechanical energy to electricity. By 2000, maintenance costs told the story clearly. Modern generators averaged $12,000 yearly in electronics repairs, software updates, and specialized technician visits. Rochester's 92-year-old machine required $1,800 for lubrication, inspection, and occasional mechanical adjustment. The efficiency advantage of high-speed operation couldn't overcome the reliability disadvantage of complex systems prone to expensive failures. The generator's 100th anniversary in 2008 attracted national attention from engineering societies and preservation groups. The machine that Thomas Garrett designed when Theodore Roosevelt was president had outlasted 15 generations of supposedly superior replacements, operating continuously through a century of technological revolution while maintaining the reliability that made it valuable from the first day it entered service. Modern engineers studying the generator discovered principles that contemporary design had forgotten. The massive cast-iron frame, criticized as wasteful in 1908, had absorbed a century of thermal cycling without the dimensional changes that destroyed lighter structures. The oversized copper windings, called unnecessarily expensive by critics, had never approached temperatures that stressed insulation or caused failures. The slow-turning rotor, dismissed as inefficient, had accumulated over 900,000 hours of operation without the bearing damage that plagued high-speed designs. The bearing journals told perhaps the most remarkable story. After a century of continuous operation, the original bronze bearings showed less than 0.015 inches of wear. The hand-scraped surfaces that Heinrich Weber created in 1908 still maintained oil films that prevented metal-to-metal contact. Modern generators with advanced bearing materials often required replacement after 50,000 hours, proving that Garrett's conservative approach achieved better results than contemporary technology. Rochester continued operating the generator not from nostalgia, but from economics. The machine still produced 2,000 kilowatts of clean, stable power at cost competitive with any modern alternative when all factors were considered. No loan payments, minimal maintenance expenses, no obsolescence concerns. The generator that seemed expensive in 1908 had become the most economical power source in the city's entire grid. Technical institutes sent students to study the installation, recognizing that fundamental engineering principles mattered more than technological sophistication. The lessons were clear: proper material selection, conservative operating speeds, oversized components, and simple mechanical systems produced better long-term results than optimization, complexity, and advanced controls. Students trained on high-speed digital equipment often failed to understand these principles that a century-old generator demonstrated perfectly. The generator's legacy extended beyond its continued operation. It proved that machines designed for durability rather than efficiency could outlast multiple generations of optimized replacements. It demonstrated that simple mechanical systems remained viable in an electronic age. Most importantly, it showed that engineering excellence meant building equipment that kept working when everything else failed. By 2020, the 112-year-old generator had become legendary among power engineers. While utilities struggled with aging, infrastructure, and expensive replacements, Rochester's ancient machine continued its steady operation, testimony to Thomas Garrett's vision that proper design transcended technological fashion. The generator sketched in 1907 had outlived its designer, his critics, and countless supposedly superior alternatives, proving that sometimes the best engineering solution is the one that simply never stops working.